Okay, let's get started. Take me a minute to get my act together here. But let's start out. Are there any questions while we're thinking about things? Any questions about anything technical or logistical? Yes. Okay, what? Volume is too high. Okay, let's see how we can solve this problem. What? Higher than before. Is this better? Okay, let's try that one. Is it still bad? No one says it's bad. Okay, any other questions? Yes. Where? What? The recorded lectures should be available on Blackboard. Has anybody actually seen evidence of the recorded lectures? Okay, I have proven that I have seen them with my own eyes, but that may mean that there isn't permission for it. Have people looked for them and failed to find them?
I've seen it. The one from 2007.
2007, no. You've looked and you couldn't find it.
Yeah, the class doesn't activate yet. Like I don't have the class in Blackboard at all.
Okay, let me say, send me mail to remind me, and I will look into that. Okay, I don't normally use Blackboard for anything, so that's why. I guess this has happened now. But we can once I can figure out how to set it, then hopefully things will be okay. Any other questions? Okay, let's get a couple of other things going. First, the first homework assignment is I want to pass out now. It's on the web. I'm just going to pass this out, so circulate that. Now, you're going to need, many of you need, okay, I want people to do the homeworks with partners. Is there anybody here who does not have a partner and wants one? Anybody who does not have a partner and wants one, I want you to stand up. Okay? Anybody who does not have a partner and wants one, I want you to stand up, look for an intelligent-looking person, and grab one. Make eye contact, me and you, okay? And then once you've made eye contact, I want you to sit down. Okay, or you can change names. Figure this out. Okay? Okay. I think people are just about ready to sit down. Give me one more second. Okay. Good. Okay, so I'm sorry it's taking me a minute to get my act together here. But let's now move on. This here, homework number 3, PDF.
I'll drop the homework off here, right?
Okay, that's where you would drop it off, yes. I haven't yet closed the books on it. Okay, let's see if we can... Okay, I'm in a somewhat alien environment now, but I want to get started because we're a little bit behind. Okay, so let's start off. We start off with the problem of the day. First of all, any technical questions about anything? Okay, then I take the problems of the day and I hide them. Okay, so they are now closed. But okay, so what is the problem of the day? I think that the problem of the day was number 222. Is that correct? Let's look at what that problem says and see if we can make sense of it. The problem has to do with comparing whether certain given pairs of functions, are they big O, big omega, or big theta relationship? And the way that we would do it is, I guess if I look at the problems, problem A says we want to know how does f of n, which is equal to n squared plus 3n plus 4, how does that compare to g of n, which is equal to 6n plus 7? Okay? And the question is, do we have a big O relationship? Do we have a big omega relationship? Do we have a big theta relationship? Now, how do we do a problem like this? I find these things very complicated. The only way that I can do these is I go back to the definition. So if it is going to be f of n, if we want to ask the question, is it big O of g of n? What does that mean? Okay? The definition says what? Okay, if there's a big O relationship here, what does that mean? It means that there exists some constant times c of n, such that this is always greater than or equal to f of n. Okay? That is what the definition is, right? And now I ask myself, is there any constant I can multiply 6n plus change by to make it bigger than n squared for big N? Is there any constant I can do that for? I mean, a yes or a no when I move the hand? No. Okay, there is no constant I can multiply this by to make that bigger, right? So that means no big O. Does everybody see that? Okay. Let's now look at the other side. What was the other one we might ask about? We might ask about, what about the omega? And what does omega mean? Omega means that there is a constant such that this side is going to be bigger than that side, right? Is there any constant c that for a large enough value of n, this function is going to be bigger than that? Is there any such constant? Yes. What would be a good example of such a constant? Well, 1, I guess, okay? That by the time you get up to something like 6 times n here is going to be like 6 times n here. And by the time you get up to 100, this is going to be 100 times n, because that's what n squared means, right? And this is still 6 times n. For large n, this side will beat up that side. So yes, it is the big omega. Does everybody see that? Any questions about that? Yes? Can I repeat that? Okay, so with all of these things, how you solve this thing is you go to what the definition is. The definition of the omega notation said this is omega of that if there is some constant here that is greater than 0, that when we multiply this times this, it gets bigger than this, right? That's the big test, okay? And the point being, no matter how big a constant you pick, 1 billion, 10 billion, the national debt, okay? It is still the case that n squared is going to beat 1 billion times n, right? There's no way you can win for all n by picking a large enough n by picking a big enough c, right? So therefore, so therefore we've got a omega relationship. Does everybody agree with that? But a theta relationship meant that it was both big O and big omega. We did not have the big O. There is no theta here. Any questions about that? Good. What was the second one? The second one, I can tell I've got my mic wrong, but let's keep going. The second one was talking about n log n, and comparing that to n squared, okay, minus n. Let me try the microphone again. Okay, let's try this. Maybe not try the microphone. I'll never figure that out. Okay, n squared log n is the function here, right? N times log n. I mean square root n, excuse me. N times square root n. Here we have n squared. This was f of n. This was g of n. Now, is it true that f of n is big O of g of n? If so, what would that mean? Again, these are complicated, so I go back to the definition. What is the definition of the big O notation? It means that if this is true, there exists some constant, c, such that c times this thing, n squared, is going to beat n log n, n square root n. Is there any such constant? Well, let's think about this for a second. First, what is it? Okay, let's try another marker. What is it that the square root sign looks funny? Okay, do people think square root signs look funny? What is n times square root n? Is there another way to say what that is? Yeah?
You could say that n is n to the 2/2 of a power, and the square root of n is n to the 1/2 power. So you could rewrite that as n to the 3/2 power.
What we can do is to say that this is n. This is really the same as n times square root n. N is n to the 1. Square root n is n to the 1/2. Does everybody remember that? N to the 1 times n to the 1/2 is really the same as n to the 3/2. Does everybody see that? And now, viewing it like this, the functions look more directly comparable, right? This is an n squared thing. This is an n to the 3/2, which means more than 1 and less than 2, right? Now, is there any constant such that a constant times n squared is going to be beating, n to the 3/2?
Yeah.
What would be a good constant for that?
1.
1 is one that makes it kind of obvious. Do people see that? Okay? If you're comparing it like this, n to the 3/2 and n to the squared, this another way to look at it is this would be the same as n to the 3/2 times n to the 1/2. Does everybody see that? And if you now think about canceling this, okay, if you cancel both sides, you're now asking me, is the square root of n bigger than 1? Right? And that seems pretty obvious. As n gets bigger and bigger, the square root of n is going to get more and more bigger than 1. Right? So the answer to this is yes. We have a big O. Any questions about that? Now, what about for these functions? What about for the omega? Is there an omega relationship here? Okay? Again, the only way I know how to do this is to go back to the definition. If there is an omega relationship, what does that mean? That would mean that there is some constant times n squared, such that this is always smaller than n to the 3/2. Okay? Is there any constant such that I can multiply this by such that this side is always smaller than that? If I could use 0, it would be, but I can't use 0, right? Now it's the same thing. If I divide both sides by n to the 3/2, it becomes obvious. Here I've got 1. Here I've got a constant times n to the 1/2. Now, is there any constant such that this times n to the 1/2 is going to lose to 1? And the answer is obviously not, right? So we have no omega. Does everybody see that? Any questions about that? Yes?
But isn't asking whether f of n is like thing about g, so it wouldn't be the other way around?
I'm asking, is f of n something of g of n, right?
So if we just prove that g is going to be...
Wait, well, okay, so the question is really, okay, so say this again. Let's make sure we get the directions right, because that is an important question.
Because it's asking whether f of n is the various location of g. So if we're proving that...
If f of n equaled, it's basically, we're asking is f of n, the thing on the left, big O of g of n, right? And again, that's what I'm really doing. In the f of n notation, if we say that f of n is big O of g of n, we mean that f of n is less than or equal to some constant times this. When we say that f, let's think what the meaning is here. F of n equals big O of g of n, that's saying that g of n is an upper bound on f of n. Isn't that right? If this is an upper bound on me, it's got to be bigger than me, right? I was to say Yao Ming is an upper bound of me, right? Why? Because he's bigger than me, right? And so I am. What to say? I'm big O of Yao Ming. You're right. Okay. Any questions? Yes.
This is not a big O notation, you said?
This is the big O notation. Okay. We are saying the big O notation. The direction is as I said it. Okay. So there should be nothing confusing here. Now everything I said so far is correct.
But wouldn't for one, the first column would be the f of n is equal to 1, and for g of n it's equal to 0 at that point.
Okay, if I look at my book, the way I'm looking at it, again, I find these things complicated. That's why I go to my definition. Okay? You look at what the definition of what it means to say f of n is big O of g of n. It means that there is a constant, and that the right-hand side is what is in some sense the bounding thing. The symbol O, omega, theta says what kind of bounding thing? Okay? All of this is done by mechanically going to the definition. Okay? There's some things in this algorithm, a lot of things in this course you're going to have to think about. This is one it's important you don't think about. It's one that you go to the definition, and this is just a consequence of what the definition is. Any questions about that? Yes?
So shouldn't we consider the whole function d of n, which will be n of n minus n?
Excuse me. Okay, so you're saying, what you're now saying is something you're saying, wait a second. What happened? I'm comparing this n squared term, and I'm forgetting about these lowercase things. Is that what you're asking about? I'm forgetting about the smaller parts and only worrying about the bigger parts of the function. That is an important point, okay? I will talk about why I can do that in today's lecture, okay? But the important thing here is I'm trying to figure out, compare myself in a gross sense. Am I bigger or smaller than this other function? And it's important then that I only really need to compare against the biggest part of the thing. Everything else is noise, right? If you, if you think about it, we've already have this idea that an n squared function grows faster than an n function. Is that right? So then subtracting off whether we add or subtract the smaller case thing turns out to not really matter. I'll be more formal about this in about 20 minutes. Okay? But when I do these analyses, I can forget the lower order terms. That's an important point. Because I'm only interested in the gross rate of growth. And that is determined by the big part of the function and not the little parts. Yes?
So what you're saying is you're saying that you can ignore the first symbol even. You can ignore the one case even though it goes against the formula.
Right, so I'm not going to worry about the smaller order terms. Hold that thought. We'll talk about that in a minute. Any questions about it? For the last one of these, let's just do it in edit. It's something about one here is comparing 2 to the n, which grows exponentially, minus this n squared thing, which grows, I think we all agree, much slower than n, 2 to the n. That's the left side. So 2 to the n is the dominant term. On the right side, we have n to the 4th plus n squared. N to the 4th is the thing that's growing faster, so that's what I'm going to worry about, right? But on one side, I've got a little n to the 4th. On the other side, I've got this big 2 to the n thing, okay? So in this case, which one of the formats is it like? Problem A, the big problem was the big function was the f of n. On part C, it is again the f sub n is the big one. So here we've got an omega and not a O and not a theta. Any questions about that? Okay. Okay, so if I look at these things, the way I'm reading these things, all of these problems have an f of n and a g of n. The first one we did, the one on the left, the f of n was the big one, right? And that gave us our omega, right? The one on the second one, the right side was the big one. That gave us our big O. If I look at this one over here, is the big side the f of n, or is the big side the g of n? Okay? The exponential thing is the big side, right? So that means that the relationship between these functions is the same as in the first example, which makes it an omega and not an O. Any questions? Yes?
So you're saying C is an omega?
C is an omega, yes.
Thank you.
Any questions? Okay, let's go and make some of this hopefully a little clearer when I start talking about dominance. Okay, so let's try to move this down a little bit. Zoom, zoom, zoom. First, let me make clearer why I care about this. Okay? So, we're going to talk, why are we talking about the big O in the first place? On one level, it's a notation for talking about functions, and we can talk about any functions this way. And in fact, I'll talk about a very strange function using the big O ideas, okay, at the end of class. The main reason we're going to be caring about this is this is, of course, on algorithms. We care about the efficiency of algorithms. One way to think about the efficiency of algorithms is I give you a problem instance of a certain size, how much time does it take? Suppose we had an algorithm that took exactly log n steps as a function of an input of size n, or n steps, or n log n, or n squared, or 2 to the n, or n factorial. And we had a computer that could execute 1 billion steps a second, which is maybe or may not be true for your computer, okay? Doesn't really matter. But let's get an arm waving a feel for how big an input size you can solve, okay? You can hope to do with a problem of that size. So let me see if I can do this thing. Suppose, let's say, we have an algorithm that takes order n time, n steps, and it can do, to solve a problem of size n, and you can do 1 billion steps a second, okay? Then, sure enough, okay, again, maybe my timing is wrong, but at some point, because where's that 1 second, okay? Here, after 1 second, you can do an instance of size 1 billion. Does everybody see what I'm doing here? It should be clear that for a problem of, if you have an algorithm that takes order n time, problems of size up to 1 billion are something you can hope to do in a reasonable amount of time. Does everybody see that? Now, what if you have a problem, an algorithm that runs in n squared time? Actually, what's an algorithm problem that takes order n time? Does anybody ever seen a problem that takes order n time? Yes?
Searching through a list by checking each element.
Searching through an unsorted array, let's say, right?
Yeah.
One of the elements in here is number 15. Go through the elements 1 through n. Are you equal to 15? Are you equal to 15, right? This tells me, even if I have a billion element array, I can hope to finish the job in 1 second. Okay? That's not bad. Okay? Of course, when you compare it to an algorithm that takes log n time, now we're talking about something that's still being measured in microseconds, right? So log n is much worse, much better as a running time than n. What here do you guys know about that takes a way of searching through an array that takes log n time? Binary search, right? So the bottom line here is, for searching through big arrays, yes, you could do it by linear search, right? If that's all you want to do, and you only want to do it once and you're willing to wait a second, right? But if you're going to be doing a lot of searches, or if you're going to be, wanting to do it faster, you need something that is asymptotically better, like log n here. More to the point, let's say we were going to do something that was quadratic, okay? Something like what is an algorithm that you guys know that takes order n squared, okay? Does anybody have an algorithm for that? Yeah? Selection sort, okay? If you took that 1 billion element arrays, you use this fast computer you got, it will now take you 31 years to do your selection sort on 1 billion things. Does everybody get this idea? This is a big difference, right? 1 second, 31 years, right? And the reason is because it is growing quadratically in the size of the input, right? Every time you double the input size, the running time will take 4 times as long. That's really what quadratic means, right? Linear means you double the input size, it takes twice as long, right? So the important point here, and when you look at some of the other complexity functions we're going to see in here, something like 2 to the n, that's an exponential thing, okay? By the time you're talking about an input of size 100, any algorithm that runs in 2 to the n time will be using 10 to the 13th years, okay, by the time you've got 100 elements in it, okay? And any time you have an algorithm that takes n factorial time, like our worst case backtracking search for traveling salesmen, by the time you've got 30 elements, you're already up to 10 to the 15th years, okay? The reason we're going to care about the big O notation is that there sort of are these sharply defined complexities of algorithms. And going from one class to another makes a big, big difference, right? It's not a question of, oh, my algorithm is twice as fast as yours. We don't care about twice as fast. Twice as fast is like multiplying it by 2. That's multiplying by a constant. That doesn't change the big O-ness of anything, right? But on the other hand, changing one of these complexity classes, saying I had an n squared algorithm and now it's n log n, well, that's a big difference. Your selection sort took n squared, that took 31 years on 1 billion entries. If you use an n log n algorithm like we're going to talk about in here, that instead took 30 seconds, okay? And that's why we're going to worry it here about big O-ness. Okay, and trying to reduce the worst case complexity. Because for large enough things, the complexity is going to make a big difference. Okay? Any questions about that? Okay? It's important to understand why we're doing this. Okay? And why this is the right way to talk about the algorithm. And if you're talking about the constants, oh, mine is 6 times n squared. No, mine's 3 times n squared. You're not talking at a level of granularity that's talking to us, that worries to us. You're talking about peanuts, okay? Where we're interested in the big gain for big N. Any questions? Okay? Good. Let's see if we can move on here. Actually, what happens if I do this? Okay, that's what happens. Let's see if I can clear it. Bunk. Okay. So what are these? I basically talked about this. What are the implications of this kind of notion? So there is this notion here that when we talk about the different kinds of functions that come up in big O notation, certain functions are bigger than another. Okay? In particular, we talk about one function, f of n, as dominating another. Okay? If it grows bigger in a, let's say, big O sense, okay, in this sort of asymptotic sense that we're talking about. So when is it that f of n dominates g of n? Okay? F of n dominates g of n if the limit of f of n over g of n, okay, goes to 0. Let's think what that means. If we have the functions, trouble, n squared and n over n cubed. What is the limit of n squared over n cubed as n goes to 0, goes to infinity? Okay, well, to simplify it, that's the same as 1 over n. Is that right? And as n gets bigger and bigger, it should be clear that those things go to the limit. As this thing goes to n equals infinity, that limit goes to 0. Does everybody see that? So these are, one function grows much faster than the other in a dominating sense. What happens, on the other hand, if I compare, maybe I'll come back to this thing again, clear ink. What happens if I compare 2n squared, okay, over, let's say, 1,000,000n squared, 100n squared? What is the limit of this as n gets bigger? This thing, as n gets big enough, what is the limit of this going to be? Yeah? 1? Well, let's simplify the function. We cancel the n squareds. This is going to be 1 over 50. Does everybody see that? So as n gets larger and larger, these things not going to go to 0, right? This is going to a constant bigger than 0. That means that this guy's not really dominating it, right? Okay? In this case, again, Yao Ming is bigger than me, but he doesn't dominate me, right? The Eiffel Tower dominates me, right? Or to be precise, when the limit here goes to 0, okay? That's what it means for dominating. And different functions as n gets larger is what it takes to be dominating. Okay? Any questions? Yes?
What's the difference between omega and little o?
What's the difference between omega and little o? Okay? So first question, does everybody see what I mean by dominates it? This is a definition. This is a definition to remember and read and to tell how you can use this to tell if one function dominates another. Right? It's just a limit test. Okay? Any questions about that before I answer your question? Yes?
You also say that the limit converges to a constant which is 0, right?
It's so long as the limit converges, it's a question, it's so long as the limit converges to 0, then one dominates the other. If it converges to a constant bigger than 0, then they are the same, they're not dominating. Yao Ming and I are both people, right? We neither of us is dominating each other in that sense. Okay? Any questions here? Okay? Again, forget the basketball player analogy. The important thing is the definition. Okay? Any questions? Now there is one question of, what does little o mean? Here I have this other complexity function that we haven't talked about yet, called little o. See that little o? Okay? Little o means grows strictly slower than. Okay? That means that if we say that f of n is little o of g of n, then that means that it is beaten up by f of n. It is dominated by g of n. Right? Okay, so let's see what this means. Again, I find I have to go to the definition, because these are always very complicated. Let's go back and clear the ink. We've talked about big O. Big O, we said, let's maybe draw a picture again. I also find pictures are very useful here. Here, a big O was an upper bound, right? That meant everything below it, right? Omega was an upper bound. It meant everything above it, right? The little o means strictly grows slower than, okay? Meaning that there can't be ties, okay? It's one about being beaten up on by something, okay? So when we take a look at, comparing it to let's take a look at this. Is n squared big O of n squared? That was a big O. The answer is yes, right? Is n big O of n squared? Is that true? Yes. Okay. Now let's change this to little o. Okay. Is n, does that grow strictly slower than n squared? Yes, it does, right? Does n squared grow strictly slower than n squared? Okay? And the answer is no. Okay? So the little o means that it grows, that the right side grows, the left side grows slower than the right side. Not just that it's slower than or equal to. Okay? Does that make sense now? Not you seeing people, how many people are happy with that? How many people are not yet happy with that? A bunch of people, okay?
The constant c can be lower than 1.
Okay. What it means is, the way I'm thinking about this is, the little o means that it's, remember we see that little o is the same as defined by here. If g of n, okay, over f of n, the limit goes to 0. That's the same as saying g of n is little o of f of n. Right? So read the definition. It's hard for me to pronounce it, but read the definition. Let's look at these cases. Suppose we have this example over here, where we had, in this case, g of n was equal to n, and f of n was n squared. If we have n over n squared, what's the limit of that as n gets bigger? It goes to 0, right? So that is saying that g of n grows much strictly slower than n squared, right? What happened if we compared n squared with n squared? Okay, let's try to clear it. Let's keep trying to do this. Okay, hold on. Now we're in trouble. Clearing. Now let's try the other case. What happens if we took n squared over n squared? The limit here, as n goes to infinity, is going to be 1, right? So there is not, the limit does not go to 0. Okay? So the way I read little o, it means not only is f of n an upper bound to you, but it is kicking your butt. Okay? It is dominating you. Right? And it's not the same. Right? That's what little o means here. How many people understand what little o means? Okay, good. Any questions about that? Yes?
So two functions are in little o relationship, which means they cannot be a theta algorithm.
Right, so the question is, what does little o mean for theta? Theta means the two functions are the same, right? Little o means that one is beating up on the other. They can't be the same and have one beat up on it, right? So those are a contradiction. Exactly right. Any questions about that? Okay? So we are going to be interested because there's certain functions that are the things that algorithms, complexities tend to be defined by, that come up often and over and over. Okay? And so we're interested in breaking the possible time complexities into different classes where we think these algorithms are essentially the same. Okay? Any questions? Okay, there were questions earlier about why did I ignore things? Okay? Let's think what this meant. We say that a function, let's just see if these make sense. I'll say that n sub a dominates n sub b if a is bigger than b. Right? This is the logic that I use to say that n cubed dominates, okay, n squared. Right? You have two functions, both of which are n to some power. If the power is different, okay, the one with the bigger power is the dominant function. Okay? Why is that? Well, what is the limit of n to the a over n to the b? That is the limit of n to the b minus a, so long as a is bigger than b. Then this is going to go to 0. Does everybody get that idea? Okay? So if we have two algorithms where the exponents differ, in a big O sense they differ. Okay? So if I have an algorithm that takes n to the 2.800000001, and I compare that to a algorithm that is n to the 2, Note this exponent is slightly higher than the other exponent, right? That is enough to generate a big O difference, right? So if so, this algorithm, sorry, oops, I don't quite know what do we do here? Sorry, that, okay. This function, okay, this is why anyway, sorry about that. This exponent here is bigger than this exponent. Does everybody see that? If we go back to what we were trying to do, sorry about this. Okay, let's go. Okay, I will try to get myself set up better next class. Clear ink. Okay, that was supposed to clear the ink, right? Now we're in good shape, right? Hold on. Clear ink. Good. Let's come back to this thing. Okay? So what I'm trying to say is that if you believe the math we said, the definition of dominance is given by the difference in exponents, then one algorithm with a slightly higher exponent on it, 2.00001, is much worse than one that is 2 to the 0 n to the 2. Okay? Any questions about that? Okay, I know I just got confused with all this stuff. How many people understand what I'm saying at this point? How many people don't feel they understand it? Okay? If you understand the notion of dominance, okay, and then this should be obvious, okay, because it's just a question of go back to the definition of what the limits mean, right? And I can tell you that as we write this, about a year ago, there was excitement in the algorithms world, okay? There was a problem, and many of you, everyone here should have taken linear algebra on some level. Remember when you multiplied matrices, right? How many people here know what I mean by matrix multiplication? Okay? Does anybody know, the standard matrix multiplication algorithm? If I give you an n matrix, n by n matrix, and multiply it by an n by n matrix, does anybody know how fast that algorithm is?
I believe it's n cubed, isn't it?
It is n cubed, and if you don't see that, let me try to explain why. If you have an n by n matrix and you multiply it by an n by n matrix, what do you get? An n by n matrix. Does everybody agree with it? And for each one of these things you get, what did you do to get that numbers? You did a dot product of that row of n numbers with that column of n numbers, right? So you did n squared times, you did a thing that involved n multiplications and additions, right? So that algorithm, which you all learned about in high school, in fact takes n cubed time. If you don't believe me, we'll talk more about it later. There was a faster algorithm, though, that they developed that's very, very clever, that takes something like n to the 2.378 something or other. And last year, someone lowered the something or other by 0.0001, okay? And this was enough for this person to become famous, okay? Why? Well, famous is a relative term, okay? In the algorithms world, this person can now strut around, right? Okay? But why was it important? It was important because there was a dominance difference here, right? The old one was 2.378, ... The new one was 2.377, right? N to the this, n to the this. This one is asymptotically better than that, right? So that is enough for that to be a breakthrough. The hope is they can do better than that too. But any questions about it? It should be clear that if we care about algorithm dominance, this thing, which seems like a minor change, is in fact a big difference. Whereas if you go and show me, look, my matrix multiplication program is twice as fast as hers, no one would pay any attention. Because as n gets larger and larger, there is no dominance difference if yours runs half as fast as before. Any questions? Okay. The other question that I wanted to go through, which is to answer the question that you had here, was what about smaller terms? Why is it that when I had a function like n squared plus n, why is it that when I was trying to analyze it, I sort of ignored these terms? Okay? I said just take the biggest term and reason about that. Well, why is that? Well, if you think that I'm caring about dominance, it should kind of be obvious. Suppose I have n squared plus n, and I want to compare that to n squared. Is it true that n squared plus n, what is the limit of n squared over n squared plus n? Okay? You see what this thing is? Yeah. What is that going to go to? As n gets larger, this thing is going to be n squared. This is going to be n squared plus n, right? As n gets larger, what does that limit go to? 1. Try this on a pocket calculator if you're confused, right? Does anybody have a pocket calculator? What is the ratio here for n equals 1,000,000? Does anyone have a calculator? Do 1,000,000 squared over 1,000,000 squared plus 1,000,000. Somebody with a calculator at a hand, then tell me what they came up with. It's going to be something like 0.9999, right? Okay? And the reason is just because of the limits. As n gets larger and larger, this small potatoes thing is going to fade away, leaving the big piece here and the big piece here. Any questions about that? Yes?
But you just said that we consider 0.00001 to be a big thing. So is it that small thing?
So the question is, where is the big thing and where is the small thing? That's a good thing. And the answer is it's not what the number is, it's where the number is. Okay? If the number is in an exponent, okay, n to the 1.9999. If we do this over, let's just take a look at this, over n to the 2.000, right? We've got a very, very small number difference here, right? But note that it's in the exponent, right? So if we took what is this divided by that, that is going to be n to the 0.000001. Do you see that? And now this function has the property that as n gets bigger and bigger and bigger, this number function is going to get bigger and bigger and bigger. Right? Again, really, I guess when we did the ratio, this should be 1 over it. Right? Okay, back. Forget it. Okay, bad news. Okay, this is why okay. This function here, because n to the 0.00001 gets larger as n gets bigger, 1 over that thing keeps getting smaller and smaller and smaller and goes to 0. Right? So a small difference in the exponent is a big deal. Right? A big thing, when you add it up next to it, is not a big deal. If we compare, what is the ratio of n over n plus 1,000,000? There we've got a big number, right? As n gets bigger, okay, this is going to, what's this number going to go to? As n gets larger and larger and larger, what's the limit of this going to go to? 1. Right? The limit of this goes to 0. The limit of this goes to 1. Okay? That's why we're going to be worried about differences in exponents. But we are not going to be worried about lower order additive terms. Does that make sense now? Any questions about that? Because this is an important point. This is why when I'm reasoning about algorithms, I'm only going to worry about the big thing that's happening. Okay? Because the lower order terms are just going to be noise. Okay? Any questions about it? Okay? Let me go back to my lecture and I'll see if I can find it again. Yeah. Again, I'm sorry about my mechanical problems here. There are a couple of reasons for this, which hopefully I'll address for future classes. Okay. So when you believe all this, there are a small number of different function types that we are going to have to get familiar in here, because we're going to see them over and over and over again, because there are a lot of algorithms that have this kind of complexity. Okay? In particular, let's look at them. One function is order 1, a constant. Can anybody think of an algorithm that takes constant time? Okay, yeah?
The left test.
The left test, well, let's think of a simpler one. I think adding two numbers together. Does everybody agree with that? So adding two numbers together takes one step. Okay? We also have algorithms in here that take log n time. We said that was binary search, right? We said here that there's algorithms that take order n time. That's like sweeping through an array of n elements, right? Look at each element, 1, 2, 3, 4, up to n. We have algorithms that take n log n time. What's an example of that? Heap sort, some of these sorting algorithms you'll see, you believe, take n log n time. We have algorithms that take n squared time. What's an example of that? We said bubble sort, selection sort, something like that. What's an algorithm that takes n cubed time? Matrix multiplication is today's favorite, right? We have algorithms that take 2 to the n time. Can anybody think of an algorithm that takes 2 to the n time? Yes.
Enumerating the power set of a certain set.
Enumerating all subsets of a particular set. We think we talked about that last time. There's 2 to the n different subsets. This would have been the brute force search for our movie star scheduling problem, right? And we have certain things that take n factorial time. What takes n factorial time?
Enumerating permutations.
Enumerating all permutations, like what we might have done with the traveling salesman. Okay? These are going to be the bread and butter complexity functions that we deal with in this class. And the point being is if you can take an algorithm and shift it over take a problem, come up with an algorithm that was this, and move it over to one slot over to the right, you have made it wildly more efficient. Okay? And that is what we care about in here. Any questions? That is what we mean by dominance. I can tell you that if you take an advanced algorithms class, there are other complexity functions that come up that are kind of weird, a little weirder, a little more esoteric, okay? But that there's a certain range of functions that if you're really a hotshot algorithm designer, you learn about these. But the bottom line, we're not even going to talk about them now. Probably not going to talk about them all semester. But the important goal being, if we have one function that dominates another function, okay, if we can move the complexity of an algorithm from one level to a slot over to the right, we have really done something. Okay, and that is what we're trying to do in here. Any questions here? And because we're going to reason at the big O level, okay, we will know if we have done something. Yes?
That epsilon there is an arbitrarily small non-zero number.
Okay, that is supposed to be an arbitrarily small non-zero number. Okay, so don't worry about what it is. Okay, the important thing is if I tell you that there's a dominance order here, anytime you move to a lower complexity, you have got an asymptotically faster algorithm. This is a big difference. Any questions? Okay, good. Okay, so we'll think about that. The homework is going to be a bunch of problems on big O notation. Hopefully you'll get to know that better. What I want to make sure of is, again, there's two different thoughts you've got to keep in your head these days. One is this language for talking about functions and dominance and big O. That's just math notation. The other is realizing that what we really care about in here are the running times of algorithms. And so when we are going to be talking about is an algorithm big O of something, what we're really going to mentally be thinking about is a written description of an algorithm that we are going to be analyzing. And this is one thing where sometimes people, I think where students sometimes start to lose things. You're going to be saying, how do I know that big O matrix multiplication is n cubed? That's a good question. How do I know that? The reason is because in my head, again, you can't see it because it's in my head, written over here in this rectangle is a pseudocode version of matrix multiplication. What does matrix multiplication look like? Does anybody remember seeing it? It's sort of as like 4i goes from 1 to n, and 4j goes from 1 to n. And then k in there goes 1 to n, do the dot product, bop, 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 right? So I am mentally seeing that. And the act of analyzing an algorithm is looking at a piece of code, be it in your head, or if you can't see it in your head, written down, okay? And trying to understand how many steps are being done by it, okay? Any questions about that? Okay? So when I ask you, what is the complexity of this? Instead of just guessing a number, you need to be thinking about a piece of program and seeing where the loops are and where the iterations are and where the things that are taking multiple steps. Okay? Any questions? So let's, as an example here, okay, let's think about this particular piece of code. This code is for a selection sort. What is the selection sort algorithm? Again, I can't read code very easily. So when I think of a description of it, I want to think about it as at like a drawing level or a word description algorithm. What is the way that selection sort worked? I was given a bunch of numbers. 1, 6, 14. I made a linear pass through my numbers, found which was the smallest one, right? Then I swapped that with the one that was in first place. And now after one iteration, I have the smallest number in the right position and one less number in my unsorted wilderness. Does everybody remember that? So what is this algorithm doing? If you look at this pseudocode, 4i goes from 1 to n, find the minimum element. This is going to be this loop here that's going to go through the unsorted part of my array, finding the index of the minimum element, right? After I had done that loop, okay, then I was going to swap the minimum element with the first element in my unsorted turf, and then bop up to a new value of I, which was going to represent doing the next iteration. Any questions about this algorithm? Okay, what it's done, can you read it? And actually, how many of you can read it from where you're sitting? With the light, the answer may be nobody. Who can see it, read it from where they are sitting? Okay, so it was clear that the people in the last rows either are further away because they can't read it. Okay, any questions? Okay, but what's the important point here? We now understand this algorithm on a level of I can simulate it. I know what it's doing in my head. It's making n iterations, each iteration of which is sweeping through all the elements, right? How would I analyze what the complexity of this algorithm is doing? Okay? I look at the code. The main thing I'm concerned with, in general, are the loops. How many times are each loop going to go around? Right? This inner loop is going around somewhere between, goes from I minus 1 to n. If it goes from I minus 1 to n, how many times does it go around? Yeah?
It should go 1/2 n.
No. In general, if I have a loop here that is going from I minus 1 to n, how many times does it go around? n minus I plus 1 minus 1, that's complicated. But I don't have to worry about that because I'm thinking at a big O level, right? If something is going around n minus I times, big O means upper bound, right? If it's going around n minus I times, what is an upper bound on n minus I? N. Does everybody see that? By just thinking in terms of an upper bound, this loop is going to go around order n, take order n time each time. If I was very big, it would be less, right? If I was very small, it would be n, right? This thing is nested within another loop. This loop is going to go around, actually, exactly n times. Does everybody see that? So what is the running time of this algorithm? Well, let's think about it. How many steps does it take to do a min? Take the min and copy the index.
Constant.
1, okay? How much does it take to swap two variables? How much time does that take? Constant, right? That takes something like 3 steps, but 3 is 1 is the same to me, right? So this is 1 plus n plus 1. What is 1 plus n plus 1? N, okay? Because I'm only thinking about this in the big O-ness sense, right? And if I have something that is taking order n time, and I'm doing it n times, that means that this is going to be order n squared. Does everybody see that? My reasoning is the reasoning of an upper bound. I am doing at most n things. Each one of these things is going to take at most n time. At most n times at most n is at most n squared. And that is the reasoning that I do here. Any questions about that? So when you say, where does the big O analysis come from? It comes from having a mental vision of a program, of a pseudocode, okay, and reasoning about it. Any questions about that? For this reason, it is good to write things down and to reason about something that you've written down carefully enough that you can think about it. Any questions? Especially as a beginning algorithm designer. Okay, I've done this enough, I can keep certain things in my head that you guys probably can't yet keep in your head. Okay? But the argument here is you write down your algorithm and then you reason about what the loops are. Any questions about it? Some programs we'll see get more subtle, okay, but that's the basic first step. Any questions? Another way to analyze an algorithm, again, that's why we talk about worst case. The outer loop goes around exactly n times. The inner loop goes around at most n times each time. N times at most n is at most n squared. At most n squared is what we mean by big O of n squared. Any questions about that? Okay. And again, I heard somebody mumbling back there about something saying, oh, I think it's a half n squared, right? Why did he think selection sort in fact took a half n squared? Well, he went back and looked at it and said, wait a second, let's go back here, okay? You said this was going around exactly n times. This loop in here is going to go around n minus I times, right? When I is small, that meaning the first when I is 1, that's n. When I is n, that means 0, right? So you might say, well, what's the average value of I here? On average, half of that time. If you're going through all values from I goes from 1 to n, you're going to be going around this inner loop, all values from 0 to n minus 1. On average, it's the middle point, which is something like n over 2. Right? So you
care about a multiplicative factor.
So you might say this is n times n over 2, so it's really n squared over 2. Okay? You might say that, but in general I'm not going to say that because I don't care about the difference between n squared and n over 2. N squared over 2. Right? It's just a multiplicative constant. Big O-wise, you got no credit for that, right? Now, if you had a sorting algorithm that ran an n to the 1.99999 time, then that's progress, right? Fortunately, n log n is even better progress, okay? Any questions about that? Any questions about how we reduce an algorithm to a complexity time? Any questions? Okay. I'd like to talk about one other thing today. And this is, I want you maybe to clear your heads a little bit, because it is a slightly different topic. But it's an important topic, and I want people to make sure they know this. It has to do with what a logarithm is. How many people in here at one point knew what a logarithm was? Most people. How many people still feel they know what a logarithm is? Most of you. Okay, but I noticed a lot of you didn't hold up your hands in the first place. Right? What is a logarithm? Okay, someone with a definition. What is a logarithm?
A logarithm is the number of times, it's the inverse of an exponent.
It is the important word of what a logarithm is. It is an inverse exponential function. What is an exponential function? Saying y equals b to the x. Okay, maybe you would write it like that. Y equals b to the x. B to the x is an exponential function. Right? If x is the variable and b is a constant, this is like 2 to the n. Right? 3 to the n is an exponential thing. If the variable is up in the exponent, that is what we mean by an exponential function. Right? So, on one level, what a logarithm is given simply by this definition. If you have something where you say y is equal to b to the x, that is the same thing as saying x is equal to the log base b of y. Okay? So in some sense, the exponent is the logarithm. Okay? It's a way to think about it. So this is equivalent notation. Notice this has 3 variables, b, x, and y. This thing has 3 variables, b, x, and y. Does everybody see that? Turns out this equation is the same thing as saying this way. Okay? Any questions about that? Got to remember what that definition is. Okay? But what is the take-home lesson here? Because that, I think, is maybe even more important to understand. Okay? Logarithms, let's say we think about base 2. Let's say b equals 2. If we say that y equals 2 to the x, okay? Okay, sorry about that. Okay? If we say y equals 2 to the x is really saying how many times do you have to double a number to get it equal to y? Okay? Let me write this down again because this is actually important. And maybe we'll just say it here. Let's think about base equals 2, b equals 2. Then what logs are really about are about how many times you have to double something to get to n, or to have something to get down to 1. Okay? That's the important lesson here. Okay? So if you want to say, what does y equals 2 to the x mean? Okay? X is going to be the number of times you must start with 1 and keep doubling it until you get to y. Does everybody see what that equation is saying? Y equals 2 to the x is how many times do you have to double something to get it to y, right? Or another way to look at it, it's how many times do you have to take y and have it to get it down to 1. Does everybody see that? How many times do you have to take 64? Okay, bad. 64. How many times do you have to have 64 to get it down to 1? 6. Why is that? Because the log base 2 of 64 is 6. Okay? Any questions about that? Okay, let's go back to the slide again if I can get it. Boom. And let's get rid of the ink. Boom. So why does this matter? In this class, we're going to see a lot of algorithm functions, a lot of complexity functions that involve logarithms. And what I can guarantee you is, many of you are going to say, where did that log come from? And I'm telling you now where that log came from. The logarithm is how many times did we have something, or how many times did we double something to get it to where we want it to be, right? Any questions about that? That is where logs come up from. They don't magically pop out of algebra. They're a weird-looking function. But their meaning is how many times do you have something, or how many times do you double something to move between 1 and n? Any questions about that? Let's look at an example here. You guys all knew binary search took log n time. What was binary search? You start with n things. These were sorted things, like names in a telephone book. You look at the middle name in the telephone book. You want to find Skeena in the telephone book. You look, it's Monroe. Which side of the telephone book is Skeena in? Skeena is greater than Monroe, right? That means it's on the right side of my finger, right? And in one step, what have I done?
Cut out half the phone book.
I have halved the telephone book. Does everybody see that? I ripped the telephone book threw half of it away, right? How many times do I take something of length n? How many times do I have it until it is down to one thing? How many times? Didn't hear that. How many times?
Log n.
Log n. Why is it log n? It's the number of times that you have something of length n and you have it until you're down to one name. Is that correct? Okay, let's look at another example here. In trees, you guys are probably familiar with binary trees. Okay? Let's draw a picture of a binary tree. Here we've got a binary tree with one leaf. Is that right? Now, let's make a taller tree. This has now how many leaves? 2. Let's make an even taller tree. How many leaves does it have? How many? 4. Does everybody agree with that? Now, suppose I have a tree here where I've got n leaves. How tall was my tree? Okay? Notice that every time I made my tree one level taller, what happened to the number of leaves? It doubled. Is that right? How many leaves would be on the next level after 4? How many leaves would I have on the next level tree? 8. And how much would be on the next level tree?
16.
And how many would be on the next level tree?
32.
And how many levels would I need to go before I got n leaves? How many levels? Log n. And why is it log n? Because log n is how many times do I have to double something until I get to n. Does everybody see that? This is where the log is coming from. You guys are going to be trying to do algebra and saying, where's that log? I don't know. This is where the log comes from. Any questions about that? Let's look at another problem. Okay, suppose, let's say, I wanted to have a computer that was capable of dealing with numbers up to size 2 to the n. Okay? Let's say that if you have a computer, okay, computers have a certain number of bits in each word, right? And they can represent the number 0 times 2 to the number of bits minus 1. Does everybody realize that? If you have a 1-bit computer, what numbers can you represent in a 1-bit computer?
0 or 1.
0 or 1. How many numbers can you represent in a 2-bit computer?
4.
4. Why is that? Because that's basically you're going 1 and you double it with every bit. When you have 3 bits, how many numbers can you represent? 8. So if I want to represent the numbers from 0 to n in my computer, How many bits of word length do I need in order to represent numbers as big, integers as big as n? How many? I need to represent log n bits. Does everybody see that? Or, if I have n bits, equivalently, I can represent the number how big? 2 to the n. Does everybody see that? So where did the log come from? Why isn't there algebra that I'm pulling the log out of? Yeah?
Because each place value has 2 digits in it.
The reason why it's a log is because every time I add something, one thing, it is doubling, right? It is a doubling process, okay? And the number of times I have to double something till I get to n is log n. Does everybody see that? Okay? That's an important point here. Any questions? Okay? Let's look at one last example. Actually, I'll do this stuff next class. I just want to do my cutesy example here. Here is a table, okay, that maybe some of you may have seen in the book, but which I like, which is the federal sentencing guidelines. I don't know, hopefully none of you are too familiar with this. But when you guys get convicted, if let's say you get convicted of a crime, the judge has to decide how much prison to send you to, right? And there is a book called the Federal Sentencing Guidelines that tries to give you an algorithm, in some sense, to try to figure out how bad your crime was, right? And if you look at the Federal Sentencing Guidelines, buried in there is this table related to crimes related to fraud, saying that figure out how much money they stole, and based on the amount of money they stole, how many points did they get? Right? That's what this is really saying. And again, you may not be able to read it so well, but it says if you stole up to $2,000, you get 1 point. If you steal up to $5,000, you get 2 points. $10,000, 3 points. $20,000, 4 points. $40,000, 5 points. $70,000, 6 points. What is interesting about this relationship? Okay? The points get traded in for years of jail time. Okay? So what is really interesting about this relationship? Yes? What? Well, what's important here is that to my mind of looking at it, if I look at the left column, every time you move through this, the numbers are pretty much doubling. Is that right?
Not quite.
Not quite, but in a rough sense, in a big O sense, in a sense that matters, from one level to another. Basically, the amount of money you steal doubles. And you get one more unit of punishment for every doubling of money you steal. Right? What does this mean? It means several things. If you want to compute your punishment, if you stole X dollars, how much punishment are you going to get? Log X, right? But what's the real implication of this? Should you steal a lot of money or a little money? Well, it should be clear that the more money you steal, the more punishment you will get, right? But on the other hand, it is clear it will grow very slowly with the amount of extra money you steal, right?
If you're already stealing $80 million, there's no real incentive not to steal.
Okay. So the important point here is if you're going to steal something, make the crime worth the time. Okay? And more to the point, look out for logarithmic relationships. Look out for doubling things. Because that's what we're going to see over and over again. Thanks for your attention. See you next class.
That's good.